All right, so for our group, let's think about this example one more time. We have the placebo, the missed dose, and the regular dose. What would we think that we should have for our contrast? So take a few seconds and try to think about how you would set this up, and then I'm going to walk you through how the appropriate way to do it is. All right, so my hypothesis 1 is that people who take Zicam will have a higher wellness rate than those who don't. So the placebo should be different, right? That's our control group, should be different than the other two doses, the missed dose or the regular dose. My second hypothesis, those that take a regular dose should have a higher wellness rating than those that miss a dose. So the missed should be different than the regular. Do we need to worry about whether the placebo is different than the missed? Not really. We really want to know at what level should you be taking these. So here's essentially the contrast that we have. We've got the first contrast, which is our control group, the placebo. That's this piece here. And then the other group is the missed plus the regular. And then our second contrast, once this is taken into consideration, we cannot consider this again. And so the second contrast can only essentially draw down from the second experimental group. All right, some more rules. Groups have to be coded with positive weights and compared to those with negative weights. The sum of the weights should be 0. If a group is not involved in a comparison, assign it a weight of 0. Weights assigned to groups of one chunk should be equal to the number of groups in the opposite chunk. If a group is singled out, then that group should not be used in any subsequent contrast. We're going to break this down to make it a little bit easier. So rule 1, we're setting up the two doses against each other, so that one contrast. Rule 2 says we have to have positive weights versus negative weights. Rule 5 says because there's two groups here, each gets a weight of 1. So then placebo has to have a weight of 2 because this is 1 plus 1. So placebo would have to have a weight of 2 as well. So 1 plus 1 is a positive 2, and a negative 2 adds up to 0, so that works out. And then because placebo is not being considered in the second contrast, it gets a weight of 0, and missed dose and regular dose, one's positive and one's negative. Does the positive versus the negative really matter? Not really. You just have to make sure that they're opposite of each other. I'm going to show you the Anova and the Spss Anova video, but this will at least show you a little bit more how you do that contrast. All right, so let's look at the output for the contrast. Pretty easy to understand. First column here says that we had two contrasts, and it tells us how we coded our contrast. So this is essentially placebo versus missed and regular. And then the second contrast is then missed versus regular. All right, and then the next table tells us whether or not those are significant. And we have to either assume equal variances or not assume equal variances, and you would eliminate one of these. So we would have to see what the original Anova output stated, whether or not they were equal or not. We're going to assume that they are, but when you get to Anova, you're going to be able to tell whether or not they are the same or different. We do know, we'll get there later, but there are no significant differences in variances. So we can essentially just cross out that bottom information. And then these are the significant differences that we're going to look at. So we can say contrast 1 was significant, and contrast 2 was not significant. So essentially the placebo is different than the missed and the regular. Now if you want to know, we know that they're different, but which is better? Well, you're going to have to go and look at the means of each one of those to find out which is better. And we're going to jump ahead here, but the placebo the mean for the placebo is equal to 2.2. The mean for the mist is equal to 3.2, and the mean for the regular dose is equal to 5.0. So if a value of 5 is a good wellness rating, then the 5 plus the 3.2 is essentially the mean for the combination. So the placebo is not as good as taking Zicam. So we should then take Zicam and not take nothing in order to feel better. So that's what the contrast is telling us. But it doesn't matter whether or not you take the mist dose or the regular dose. Those are essentially the same, even though 3.2 and 5 do not look the same. They are statistically the same. So that is what the contrast can tell us. All right, moving on to the post hoc. Post hoc is just comparing every mean against everything else. So you're going to throw everything at the wall. But the problem is when you're doing this, you need to figure out how many comparisons you're doing because you need to control that family-wise error. And so essentially you're going to look at the Bonferroni method, which is you're going to take your alpha value of 0.05, divide it by the number of tests, and that's what you're going to change in your ANOVA. That's what you're going to change that alpha to, is you're going to create the new Bonferroni alpha. And that's what you're going to enter in SPSS because you know you want to compare, let's say in this example, the Zicam example, you want 3 comparisons. So 0.05 divided by 3, we would be looking at an alpha of 0.017 instead of 0.05. So that's how we would actually control it. Obviously, when you start to reduce that alpha, you're going to actually lose some statistical power as well. But at least you're not increasing the probability of type 1 error rates. Just to be very confusing, SPSS has 18 different types of post hoc tests, but they're subdivided. This group up here is for if you have equal variances, and this group is if you do not have equal variances. And this is where you would change that significance level right there to the 0.017. So what happens if at this point you don't know if you have equal variances or not? You could choose one from this category and one from that category, and then after the analysis results come in, you're only going to pick one of those to look at. So you can easily pick one from each category and then proceed at this stage in the game. Now, of those 18 different tests, there's pros and cons associated with all of them. You can go and read through these yourselves. I think the most important thing to note are my recommendations. So I've taken all that information and broken it down to what should you use. So if you meet all of your assumptions, you can use the REGWQ or the Tukey. They're both excellent. Another safe option if you meet your assumptions is the Bonferroni. If you have unequal sample sizes, you can use either Gabriel's or Hochberg's, depending upon the sample size that you have. So if you have less than 10 in your sample size, you should use Gabriel's. If you have more than 10 or so, a large sample size, use Hochberg's. If you have unequal variances, always use Games-Howell. It's the one that has the most power. So that's the easy summary. It kind of eliminates the 18 to 1, 2, 3, 4, 5, 6. So 18 down to 6 options. Hopefully that makes you a little bit happier. And then the trend analysis, you can compare your data to find out whether it is a linear trend, a quadratic trend, cubic or quartic, if you wanted to do that. But again, we're not going to cover that, but those are some of the ideas that you could do. All right, so we're going to run the ANOVA. Again, look at the SPSS ANOVA to kind of see what's going on and how to choose things. And then we're going to look at the output here. All right, so this is just the descriptives. So this is where we get the information on the mean, which is going to be very critical for understanding the results. So we need this to be able to understand the results of our test. And other than that, We don't want the confidence obviously to cross 0. It doesn't. But that's really the biggest piece that you're going to pull from here is the mean information. The next output you have is whether or not your variances are homogeneous. We have a significance value of 0.9, so we have no significant difference. So we do have homogeneous variances. So because of this, we do not have to report the Welch modification. So we can just look at their traditional ANOVA. And what we can start to see is we've got the systematic, that's our between groups. If you don't do a contrast, you will not have this information in there. And the unsystematic is our within groups. And this is the linear, so this is more of our trend analysis. This in our systematic, that is what we would call our experimental effect. And then this is the information that we're really looking at to find out whether our group means are similar. So what we can say is we have a significant effect of Zicam. We do know that to be true. But at this stage in the game, we don't know which means are different. Okay? Now this is the piece that we don't need to know about. If you did have a significant difference in your heterogeneous variances, instead of looking at the previous significance, you would look at this significance, these degrees of freedom, and there is your new F statistic. But because we have homogeneous variances, we don't have to look at this. So this is only if you have heterogeneous variances, you have to look at this. All right, the contrast, we already looked at this, but we know that we don't have to look at this information. We have our contrast significance, so contrast 1. Zicam significantly increases wellness compared to the control group. Now, when we did our hypothesis, let's talk about the secondary piece. We have a significant two-tailed test. Our hypothesis was directional, right? Our hypothesis was not an equal. Our hypothesis was directional. A directional hypothesis means it is a one-tailed test. So because our contrast was actually one-tailed, for contrast 1, our significance value is actually 0.029 divided by 2, right? Because it was a one-tailed test. So our significance is actually 0.0145. Doesn't change the outcome for contrast 1, but contrast 2 was also a one-tailed test. So its significance is 0.065 divided by 2, which, guess what, changes the outcome, 0.0325. So now we have significant difference in both of them, right? Both contrast 1 and contrast 2 are significantly different. So the placebo is significantly different than the mixed and the regular dose, and the mixed dose is significantly different than the regular dose. How do you know which one is better? You have to go back to the mean data in that first descriptive table to find out which one of those two are actually better. All right, now when we look at our post hoc test, we have to make the decision, did we have equal variances? Yes, we did, which means we cannot look at this information. We have to cross it out. We can only focus on the Tukey because that is associated with homogeneous variances. And we're going to go ahead and look at these significant differences here. So the placebo versus the missed dose is a significance of 0.516. So there is no difference between the placebo and the missed dose. So the mean of the placebo is equal to the mean of the missed dose. The placebo versus the regular dose, there is a significant difference. So the placebo is not equal to the regular dose. And then we can compare the missed dose versus the regular dose, and those are essentially the same as well. So the mean of the missed dose is equal to the mean of the regular dose. Alright, so comparing the experimental groups to the placebo group, it looks like the placebo has a mean of 2.2, so we can say that by taking the regular dose is actually better than taking the placebo. But missing a dose and taking the regular dose are the same, but taking the missed dose is the same as taking the placebo. So essentially the only thing that's important is you either take nothing or you should take something, and it seems like you should take something, but it should be at a regular dosage. So this post hoc slightly contradicts our contrast, yes? And that's why we have to be very careful when we're interpreting our planned contrast. The planned contrast actually have a little bit more power than the post hoc test. So we should just consider that when we're looking at things. Alright, so why are they contradictory? Post hoc tests are all two-tailed, and the post hoc tests are more conservative, so it's less power to detect the true effects. So contrasts are better, but in order to make a one-tailed decision for the contrast, which is what you're going to have to do, you're going to have some type of previous prior information to be able to make that decision. Now the next piece, we can look at the effect size in general. So our mean divided by our model sum of squares divided by our total sum of squares says that's a decent large effect. So the effect of Zicam on wellness is substantial. However, we do have a problem with this because it's just really based upon the sum of squares. It's better to look at something that deals with more of the mean sum of squares. So we have this new element for the ANOVA called the omega squared, and it's calculated as such. And we normally report the omega squared and not the omega, and that omega squared of 0.35 is a large effect. And you can see here that the omega squared are a little bit different than our R values that we previously talked about. And then you can look at them for the contrast as well, and you find out that the contrast is also significant. All right, so from here on out, go ahead and look at the ANOVA SPSS. But that pretty much is it for the ANOVA. It's a really nice, easy test, very similar to the t-test. And hopefully it won't be too much